Welcome back to part 9 of Password Cracking 101 plus 1. So in the last episode we finished off with a keyboard walk attack where we attacked a 10 character walk on a US keyboard that changed direction 3 times using KW processor and using that to generate keyboard walk candidates that we piped into Hashcat. We're going to move on across a few different areas now before ending up at Combinator attacks for this video's exercise. So, target-specific word list generation. Okay, so this is something that everyone should be doing during tests, which is gathering target-specific word lists and using that to identify low-hanging fruit in an organisation's passwords. So, yes, don't get me wrong, we've got our go-to dictionaries and rules and whatnot, but you could use a tool like Sool from DigiNinja, which is Robin Wood, and you could scrape your target organisation's website to compile a list of words that may have some passwords in them, because people love to use words about their company. People always love using their company name or address with a token 1, 2, 3 or exclamation mark at the end, and these are all things that can be gathered from your target's website. So you could use this tool to go across the site, grab email addresses, choose a depth of your choosing depending on how sort of far into the site you want to go, and to create a word list with it. You could then unique that word list and you've now got something to start mangling with rules or whatever you want, and that can get you some extra passwords. Okay, the guidelines. So back in 2003, the National Institute for Standards and Technology, or NIST, issued guidance about passwords, and they're all things that we've all kind of, well, I won't say grown up with, but things that we've been aware of for a long time. Things like, we need to be using a minimum of 8 characters, the importance, of course, of special characters and all that kind of stuff that's been emphasised on us, and that passwords should be rotated. Okay, now the new guidance, which was issued in summer 2017 and is detailed in special publication 800-63B, has kind of said we need to don't forget the old stuff. We now need to start promoting length over complexity. Okay, so we should be supporting at least 64 characters, but very worryingly, it still says a minimum of 8. Complexity should be recommended but not required, and things like this. So we're really moving to an era where we need to be prioritising passphrases over passwords. Complexity should not be enforced, but should be encouraged at the very least. Things like taking away password hints, abolishing anything based from knowledge-based authentication, so even things like security questions. A determined attacker will not find it hard to identify your mother's maiden name, or the first car you drove, or where you first went to school, or your best friend's name, or any of this other rubbish that we kind of see when we're asked to make security questions. No expiry without justification. So this is an interesting one. Rather than rotating passwords periodically every 90 or 60 days or whenever, don't expire account unless you've got reason to believe there's a breach or something else. So if your passwords are sufficiently long in the first instance, you shouldn't really be expiring them unless you've got reason to expire them. You can do lookups to compare to dictionaries and known breaches and other things as well. There's of course a hell of a lot more than that, but for the takeaway from this slide, we want to get across that we really should be prioritising length instead of complexity. Passphrases over passwords. This XKCD comic came out around the same time, actually, in summer 2017, and I saw it on so many different websites when we were sort of reading all these new articles about how we should be choosing our passwords. And although this particular comic did focus web attacks, sort of remote online attacks, rather than hash cracking, the premise still stands. It's still the same kind of principle. That we have been kind of conditioned and nurtured into creating passwords that look like this in the top left, but we should be creating passwords that look like this in the bottom left. Not that explicit one. I have actually seen correct horse battery staple on an engagement, so don't use that explicit one. But we should be looking at lots of random words together, and you can see we've got a very good password length there as a result of those words. So with that, we can start looking to attack these passphrases, shall we say. So how can we go about doing this? With Combinator attacks, we've looked at brute force and mask and hybrid and other things. We're now going to look at Combinator attacks. And Combinator is attack mode 1 in Hashcat. So we've looked at some different attack modes already. Attack mode 1 is going to expect 2 dictionary inputs from us, 2 word lists. So the Hashcat can combine all the entries in one with all the entries in the other to make a passphrase. Okay? Now, doing that with RockU would be quite a painful task because it would be way too big to sort of generate that many different words, and you'd probably run out of disk space too when you're generating huge dictionaries. But for this example, we're going to look at something reasonable like Google's top 10,000 or 20,000 words. So it's a very base form. You could call Hashcat, tell it your mode, give it your hashes, and say in Combinator mode, I want to take every entry in the 20k text from Google and combine it with itself. And what that will do is generate all the combinations of both and effectively give you a two element passphrase, so one word from each combined. Okay, so at a raw form, that's what we're starting with. But we can build on this. We can use a binary called Combinator that comes with the Hashcat utils and use that to combine our dictionaries to make new dictionaries. Now, yes, we could use Linux to do this as well, but there are purpose-built tools out there that will take 2 inputs and just spit out a combined output, and Combinator is exactly that. And there's a few slides where I'm following this thread along, so hopefully the naming convention won't be too hard to understand. But if we take, in this example, Google's 20k.txt and combine it with itself, what I've done is I've created a dictionary called 20k combines. And when you look inside the results of that dictionary, you can see it's going to take the first word in the 20k, which is the, and combine it with the second dictionary, so it's going to be all of the same words again. And after it's done that, in this case 20,000 times, it's going to go on to the next word, which will be of, and there'll be of on the left side, and so on and so forth. And you can see how this is going to blow up very quickly into a very, very large number of combinations. With that 20k combined dictionary that I've just created, we could then attack 3 or 4 words, or 3 or 4 element passphrases, I should say. And by combining 20k combined with itself, or 20k combined with just the 20k.txt, you can see how we could get 1, 2, 3 or 1, 2, 3, 4 elements passphrases by combining an already combined dictionary. Okay, now I'm not going to sit here and say this is a fantastic attack that's going to rain clear text passwords on your Hashcat screens. It probably won't, but what it might do is open up some extra avenues of attack, and certainly might get those few elusive hashes that traditional dictionaries and rules might have missed. Okay, but what we've done so far is we've taken 4 words and we've just kind of bunched them up together. What if people are being clever? What if people are using spaces, for example, or another delimiter? Well, we can address this, okay? And there's a kind of a funkier, cleverer, more way that we're going to look at addressing this in a subsequent slide. Might even be a subsequent video, but for the time being, let's break this down in hopefully a kind of a simple way to understand. What if we took our 20k.txt file and put a space at the end of every single line? Okay, so we could use awk or anything else to do that. And in this example, we're forcefully inserting a space at the end of every line in our 20k.txt file to create a dictionary that I'm going to call 20k space. And you can see here we've got the first line, which is the, but looking at the length of that line, we've got a length 4 because there is a space at the end. Similarly, a space at the end of the word of there. Now we have a dictionary that's got a space at the end of every line. We could use this to build bigger dictionaries, to build bigger passphrases and things like this. So one example would be to use our Combinator binary from Hashcat utils to take our 20k space dictionary, the first one, and combine it with the original 20k. And as you'll imagine, it'll take the first dictionary, which is in this instance going to be the with a space at the end that we've just added in, and then bolt on the original at the end. So now we've managed to create a 2-element passphrase that is space delimited. Of course, there's no space at the end of here because we've only bolted on our 20k.txt where the line ends cleanly. So if we combine those, I've created a dictionary that's now getting quite a tongue twister here. We've now got 20k combined mid-space. Okay, so that's going to represent 2 elements with a space in the middle. So how can we bolt on some rules to this? Well, in Combinator mode, we're unfortunately a little bit limited in Hashcat. We can only assign a single rule to apply to either the left or the right dictionary in Combinator mode, and we can do that as an example shown here with the -j or the -k. In this instance, what we're doing is we're doing a combinator attack with our 20k combined mid space, and we're forcefully inserting a space, which is what this syntax is, with the J, so we're applying that to the left dictionary and then bolting on 20k afterwards. So there's our 20k combined mid space dictionary up to the second the. This space here is what's being produced by the -j insert space, and then finally our original 20k.text dictionary at the end. Similarly, we could do this with our 20k combined mid-space dictionary twice to create a 4-element passphrase, again space delimited, okay? But that is still, now we're stuck now. We can't capitalize any of this, we can't add a 1 on the end, we can't do any of that stuff because we're unfortunately limited to this single J rule whilst in combinator mode. So, how can we get around that? We can combinator all the rules by adding yet another space, okay? So, we've got our combined mid-space dictionary, which is our 2 elements and a space in the middle, and then we're going to forcefully add a space in with awk at the end of that to create 20k combined mid-end space. Of course you don't have to use these words, I'm just using this to try and keep the slides on track for how our word lists are kind of growing and expanding in each instance. So by doing this, we now have a word list that in the first line's case is the space the, but there's also a space at the end here. Okay, now we can finally build that into an attack. So what we can do is we can use our combinator binary and say take our dictionary that we've just created where there's a space in the middle and the end, and combine that with the previous dictionary we made where there's only a space in the middle. Because doing that will ensure that we have the right number of spaces and there's no trailing space at the end. We can then take all of those candidates that are going to be generated by Combinator, pipe that to hashcat, and then it's business as usual. Call your attack mode, call your hash mode, call your hashes, and now you can apply rules and do whatever you want to. And of course, work mode 4, and we'll talk about -o in a second, and that's a way to get around it. So you can still generate your candidates and then you can go about applying rules to it thereafter. Now I'm not saying that these attacks will finish quickly, depending on how big your word lists are and of course how big your rule lists you're applying are. This could run forever and a day, but it's still a way about doing it. And you might still be able to let this run for several hours or days, whatever you're willing, and see some of those hashes fall. Now this -o is optimized kernels, and we're introducing it here because we're going to talk about it in a subsequent slide. Optimized kernels allow you to, many times, dramatically increase the speed in which hashcat attacks. However, it does come at a sacrifice. It limits the maximum password length that you'll be able to test. Now, generally, for unoptimized, when you're running without -o, there are caveats to this, but generally you've got a 256 limit in terms of your passwords. And I know we're not too concerned with our users using 256 character passwords, but that is the limit nonetheless. When running with optimized kernels, the general limit is 55, but there are some exceptions, there are some use cases, and we're not going to go into those too much. But one thing I do want to draw your attention to is this screenshot at the bottom. Now, this is another blog that I wrote in my former employer that looked at maximum password length. And even though we have a general optimized limit of 55, we're not always going to be able to achieve that depending on the hashes we attack, and all the hashing algorithms we attack, and also what characters we're using to attack them with. We're not going to get too deep into this so far, but if we look at this example, and I'm actually using John for this because John presents this in a nice format, we want to look at format NT, so this is a Windows NTLM hash, and we want to look for the maximum password length supported by Windows NTLM. When running with optimized kernels, this will be, and this will apply in hashcat. I'm just using John to display the information. You'll see here that we've got a maximum password length of 27. Now that's because in Windows world it's based around UTF-16, which we did actually look at in an earlier video, and UTF-16 uses 2 bytes to store a single character. Now, as we have to use 2 bytes per character, we now no longer have 55. We have 55 over 2, we have to halve it. But as 27.5 isn't, of course, a password length, the largest integer we get from that is 27. So there is a trade-off for this, okay? When we're attacking, there is a trade-off. We're not going to get too deep into why the link length is 55. This actually boils down to how Merkle-Damgard hashes are constructed, which are MD4 and 5 and some SHA-1 and 2 hashes and things. At the end of the blocks there are padding and things which reduces the maximum number of characters we can test, and the limit we're working with, based on the Hashcat team's fantastic way of optimizing to make sure we're eking out every character we can, but within reasonable trade-off limits, has been determined to be 55. So we are looking at limitations here that are imposed on us. But yes, the sort of the TLDR version of this is 55 over 2 gives us 27.5, and because Windows uses 2 bytes per character for storing, 27 is our kind of hard limit when using optimized kernels. You can of course omit that and try and crack 28 character passwords and beyond, but you will be running at a slower speed. Similarly, for MD5, we have a 55 limit, as shown here, but we then also have a worst case UTF-8. Now, we're going to be looking at encoding a little bit more in a subsequent video, but UTF-8 supports several bytes, up to 4 bytes actually, of encoding, and in this particular instance, we've got a maximum password length supported by up to 3 byte UTF-8 characters here. So 18 times 3 is 54, that falls within our limit here, but 18 times 4 is 72, so that would be well out of our 55 limit. So this would only apply to kind of lesser used character sets, so maybe some Asian character sets, and other things often use multi-byte encoding, so UTF-8 2 or 3 byte encoding to store their characters. But generally, if we're attacking normal printable ASCII passwords, the limit would be 55. The attack mode is also important for fast hashes, okay, so this is something that's often overlooked. Whilst we do have that 55, that overarching 55 limit, we do actually have differing limits depending on the mode we're using. So in dictionary attack mode, our actual limit for fast hashes, again, using optimized kernels, is in fact 31, something to be aware of. Now, whether you're frequently looking to crack 40 character and beyond passwords, isn't an argument for today. But generally, 31 will more often than not encapsulate most of your needs for modern password cracking. It is important to be aware though, because as we look at these combinator attacks that we touched on before, we are now building into realms where longer passwords are becoming a thing. Now, that's a combinator attack, admittedly, and as you can see here, for a combinator, we do have a 31 per word list limit. Now, what does that mean per word list? So, our overarching limit of 55 applies here. If we have a combinator attack and we have let's say we have a left dictionary that has a 30 character word in it, and a right dictionary in our combinator attack that has a 20 character word in it, that would crack because they're both individually below 31, and the overarching password length of 50 falls underneath 55. We're all good. But if you had a combinator attack where the left dictionary had, let's say, a 40 character password in it, and the right dictionary had a 10 character password in it, although that 50 character password would fall under the 55 limit, we've broken the rules of the per word list limit, because 40 wouldn't be allowed. So it has to come under 55, and each individual dictionary has a limit of 31. Assuming those rules are met, it will crack. Otherwise, even if those vanilla candidates are in your word lists, Hashcat will not crack it. Again, assuming you're running optimized kernels. So, we've covered a lot in this video. Let's move on to an actual combinator attack. We've got an MD5 hash here in exercise 9, and this is a 3-element passphrase without a delimiter. So let's bring Hashcat into view, and the first thing we're going to do is we are going to use Combinator to create a combined word list. We're going to use the Google word list, which is in your word lists folder, and we're going to call Combinator bin and say take the Google word list and combine it with the Google word list. Create a new dictionary for me called Google Combined. Okay, it would help if I had the correct path for Combinator. Okay, so let's take that, run that again, and now we've got our combined dictionary. And actually, if we now look in our word lists to Google Combined, we can see about search. It's taken our Google Dictionary, combined it with itself, and as we go on, this is going to create many combinations of each one in turn. So let's use our new dictionary to attack. We are going to call hashcat. I'm not looking for the file again. We know the file we're attacking. This is exercise 9MD5 that contains the hash I've just typed. A1 Combinator mode. So we're going to take our Google combined word list with our Google word list. Now, if you think Google combined with Google, we've not done the combined twice because that would give us 4 elements. We're after a 3-element passphrase. So this dictionary is our already combined word list, and we're going to bolt on just a 3rd instance of each word. And doing that will give us every possible combination. We're running this with optimized kernels. We can see here maximum supported length is shown to be 31 there, as discussed previously. And this has cracked very, very quickly for us. An MD5 hash about caught applying. So there are 3 elements that have been concatenated together to make our 3-element passphrase. So a longer dictionary than the kind of a longer password than the kind of average one we see. Yes, it is all lowercase. But again, this might be something you want to look at to start building on, and in a 4-element passphrase form to see if there's any sort of users using passphrases in the domains that you are dumping. So with that, there is our answer. Again, you do have all of these pre-built onto your Kali VMs in the .answers folder, which is in your Kali directory, the hidden directory answers. But with that, thank you very much, and look forward to seeing you in the next video.